I hope lunch was to everybody's satisfaction. We're looking now at patient-specific factors in IOL power calculations. I do have these financial disclosures. Basically, with IOL calculation data, we like to think the more patient-specific I can get, the better I'm going to be. So that if I looked at sort of a triangle, if I started in a very naive way, one size fits all, everybody gets a 23 diopter lens, I got a few patients that might be happy, but a whole lot that probably won't be happy. And so if I can measure some characteristics of the patient, and these are the easiest, the axial length and the keratometry of the patient, then I can get a little closer to what they actually need. And I would estimate where the lens is going to sit in the eye on the basis of regression equations that sort of say, hey, you know, I missed by this much with a 24 diopter lens, I have to adjust my calculation. So I'll use regression equations to sort of get the internal aspects of the eye outside of axial length and keratometry. Or if I can, I'll measure internal characteristics of the eye like axial length, the ACD, the anterior chamber depth, as well as lens thickness. And now I'm going to estimate the effective lens position on the basis of the characteristics of that particular patient's eye. Okay, so the closer I get to the patient's actual biometry or eye geometry, the better the potential overall results. Of course, this depends on how good my measurements are as well. The most important factors for IOL calculation, it's not a surprise to anybody, axial length matters a whole lot, as does keratometry, and Warren gave a good overview of that. The third thing is, where is that intraocular lens going to sit in the eye? Okay, so this is often ignored in early generation calculations, and the reason is if I have axial length and keratometry data, I can use sort of population averages to get regression equations, and that where the lens is sitting in the eye is basically intrinsically included in my regression formula. So it accounts for the effects of the intraocular lens as well as the patient's individual biometry. So when we talk about effective lens position, it's where is that lens in the eye, but more importantly, it's where is the optical power of that lens in the eye. And so we use, in most cases, a thin lens approximation for optical purposes to say here's where the IOL is effectively sitting in the eye. And there are two things that affect it. Its actual physical position as well as the design of the intraocular lens itself. And so you'll notice when you're trying to do IOL calculations, lenses have different A constants, and that's a reflection of IOL design. So here's a lens that has a biconvex surface, and they happen to be equal. So the effective power of that lens, if I'm looking at a thin lens, is actually in the middle of that lens. But if I move that, and I don't change the power of the lens that I'm talking about, but I change so that all of its power is at the back surface, I've actually moved my focal point behind the retina. So that patient would end up hyperopic. Or if I moved and the shape of the lens was such that all the power was at the front, and it was the same power IOL, I'm going to make the patient a little myopic. So this is why lens geometry, if you like, the shape factor of the lens affects my consideration of lens position. And so what I want to do with a lens, here I've got something focused at the back. If I move the power or the shape changes, I'm actually going to end up using less power in that IOL as the shape sort of moves so that more power is at the front of the lens. So I have to adjust basically the power of my IOL based on its particular shape. Okay, so that takes care of the IOL specific factor in the eye. Now the second thing is where is the IOL actually sitting in the capsule? So no surprise here about the geometry. If I zoom in, what I'm looking at is, again, a lens is sitting in the eye. It has a certain focal point. If it sits further forward, I'm going to end up with a myopic patient. If it sits further backwards, I'm going to end up with a hyperopic patient. Now, the lens is going to generally sit in the middle of the capsule, the empty capsule. The challenge is I never know where that empty capsule is going to be. So lens thickness, for instance, can tell me something about that, and hopefully my estimate of effective lens position improves with that. So again, just as I did with the intraocular lens shape factor, what I'm going to do is adjust my lens. If my lens is sitting closer to the cornea, then I'm going to lower the power. And if my lens was sitting further back in the eye, then I'm going to increase the power so that I end up staying on the fovea. Okay? So that's all there is to IOL calculations in a sense. So I want to use patient-specific data because if I'm accurate and precise with the measurements of a particular eye, I should be better than the population average. You know, the regression formulas basically count on population averages. Now, the only caveat to that is if I've got really lousy measurements for individuals, then the population average may be a better way to go. So I need an instrument that's giving me precise and accurate data. Luckily, there's the LensStar LS900 to do that for us. It's an optical low coherence reflectometer. It gives me keratometry. It gives me axial length. You saw from Warren's presentation the keratometry is high density. Axial length is optical. I get the anterior chamber depth. I get lens thickness, and it will measure from an eye image the white to white. Okay? So what we did to test the various IOL power calculation formulas with the LensStar LS900 was take 628 eyes out of 424 patients who were measured with the LensStar preoperatively, had an IOL power calculated, and a lens implanted, and then we got their postoperative refractive results. So from the postoperative refraction data, I can sit there and go, I missed by this much, I should have put this lens in. So basically, by doing some back calculating optics, I can tell what the best power should have been in that patient's eye. The other thing I can do on the basis of my results is optimize my lens constant, or optimize my formula. Okay, because I can take a regression and say, ooh, I missed by this much, I'm going to adjust my average A constants by this much to give me a better power calculation. So that if I do that, the mean of that population I use should be 0. Like the mean error should be 0 when I've made that adjustment. Now, it doesn't affect the patient, but it affects my math after the fact. So now I know what the best lens is, and I know what the optimal formula is for those eyes. So I can repeat all my IOL calculations using this optimized formula and compare the lens it suggests to the best lens that I already know from their post-op refraction. So this is what we did with 5 different formulas. You can see them there, the SRKT, Hoffer Q, Holiday 1. And those 3 formulas use only Ks and axial length for their measurements. The rest is based on regression. So Holiday 2 and the Olsen formula include consideration of the anterior chamber depth of that patient, the lens thickness of that patient, and in Holiday 2's case, white to white age and the preoperative prescription, and with Olsen, the horizontal white to white. So here are the measurements of the anterior chamber depth across those 628 eyes. Okay, we have a mean value of about 3 diopters and a standard deviation of 0.5. So the maximum anterior chamber depth is almost twice or just over twice the minimum anterior chamber depth. Okay, so there's a fair bit of variability in that. It is correlated to axial length and Ks, but having the individual patient numbers means I don't have to count on a population average. The same thing is true with lens thickness. I have 628 lens thickness measurements. The mean is just over 4.6 millimeters, but the standard deviation is almost 0.5. So again, the maximum value is nearly twice the minimum value. So I'm getting measurable differences, if you like, in lens thickness. So now we make all the calculations. We know what the best IOL is, and we subtract away the results from my IOL calculations from this best IOL. And what it does is give me a power calculation error. So it tells me how much did I miss by on average on that population. Now, because I optimized my constants, it's no surprise at all that the median value is really close to 0. I mean, if it didn't, I'd have to go back and redo my mathematics. The formula are listed here. The box, the bigger box, is the middle 80% of my patients. Okay? And the ends of the T's are the maxima and minima. So it shows you for those 5 formula that generally getting 80% of my eyes within 0.5 diopter is quite feasible with all of them, but you can see the 2 on the right look like they might have slightly smaller boxes there. And in fact, that is indeed the case. When I look at the residual refractive error by formula, I can look at the percentage of eyes within a certain dioptric equivalent of the target. And in fact, the last two, if you look at the within half a diopter of target, Holiday 2 and Olson show a higher percentage, and this was statistically significantly higher, of patients within a half. And then as we get to larger spreads, then the sort of population average takes over and is reasonable, so all of the formula performed pretty well within 3/4 and within 1. So we are talking about incremental improvements here. And the strange thing is I still get a 0.5% to 1% refractive surprises. So if I was just going to summarize the optimized power calculations, all of them are providing reasonable results, and there are refractive surprises with all the formulas. Now, one of the things that we might think matters more than we would have thought is the effects of dry eye, because it can really affect our measurements of keratometry, whether I'm using a topographer, an autokeratometer. Also, there can be pupil size and corneal asphericity effects that change the patient's perceived refraction, and so the difference I'm calculating here may be a little variable. I have unmeasured effects like posterior corneal astigmatism, and then of course there are certainly measurement limitations to all the devices. But anything I've done, the formula changes are incremental, so I'm not going to see a revolution, or it's unlikely in the near future. What I want to do is just keep growing that population of patients that are within a half a diopter, because those tend to be pretty darn happy customers. So Olson uses a relative percentage of lens thickness in his formula to calculate where I should be. Holiday 2 does not, but it uses lens thickness as a parameter in its multiple regression. The nice thing is, between those two, when I look at their optimized power calculation errors, there's no statistically significant difference between the two formulas when I use the lens star to measure the raw data. So this evaluation was based on a really large data set, 600 eyes, which surprisingly enough is a really large data set when you try to get clean data. The two formulas here, Holiday 2 and Olson, that contained more patient-specific factors like the anterior chamber depth and the lens thickness, had a significantly higher percentage of patients within a half a diopter of target than the other less detailed formula when the formula are optimized with the available data. So better results with more detailed formulas depend on, again, reliable patient-specific data. So I want to use patient data. I need it to be reliable. Measurements have to have that accuracy and precision, but then I can move an even higher percentage of patients into that plus or minus half diopter range. Thank you.